This is the video solution for problem number 95 from the textbook. We're given a spherical shell with an inside radius of r and an outside radius of 2r, and the stress tensor of rho over 3 little r times the quantity 1 minus 8 times capital R cubed over little r cubed x tensor x, where rho is the magnetic constant of our shell, x is the position vector, r is the radial distance to the point x, and is defined as the square root of x dot x, and the partial derivative of r with respect to xj equals xj divided by little r. For this problem, we were first asked to find the body force vector for our shell, and in order to determine this, we will need to know what the Sij quantity of this vector is. So we know what xs with respect to x is equal to. For x tensor x, we substitute xi ei tensor xj ej. We gather up our constants, and we come up with this quantity in the brackets is our Sij component with ei tensor ej. Since we know our Sij function, to simplify our partial derivative for our divergence, we are going to create a function f, which is equal to rho over 3 little r times the quantity 1 minus 8 capital R cubed over little r cubed. The partial derivative of this function with respect to xk, and we get this quantity after using the partial derivative r with respect to xk equals to xk over r provided in our problem statement. From here, we simplify and get our final solution of partial derivative of f with respect to xk is this equation. Now, to find our divergence and the partial derivative of Sij with respect to xj, we find the partial derivative of f with respect to x, holding x1 and xj constant, plus the partial derivative of xi with respect to xj, holding f and xj constant, plus the partial derivative of xj with respect to xj, holding f and xi constant, providing this function. Now we can simplify because we know xj times xj is equal to little r squared. We also know that with our delta ij, I is equal to j, and this xj becomes an xi. And then substituting and simplifying, we get the following for the partial derivative of Sij with respect to xj. Again, we know that the divergence of s plus b is equal to 0, and therefore b is equal to the negative divergence of s, which is equal to the negative partial derivative of Sij with respect to xj, and we get this final solution for our body force vector. The question then asks us to find the pressure at the inside surface of the shell. We know that Sij is this function, and for the internal pressure, little r is equal to r from what was given to us in the problem statement. Therefore, we substitute this value in to our Sij function and simplify and get a final value of negative 7 rho over 3 capital R xi xj. Finally, the problem statement asks us to find the tractions if we take a slice of the sphere at x3 is equal to 0. So to find a traction, we know that the function of our stress tensor S is a function that is a function of r, x tensor x. So therefore, S operating on n, our normal vector, would equal this statement. Simplifying, we know that our traction would be our function f times the vector x dotted with the normal vector operating on x. Inside the shell, we know that our normal vector is equal to negative x over little r, so we substitute this value into our traction equation. We know that x dot x is equal to little r squared. We simplify and substitute in our function f to get this quantity. At the inner shell, we know that little r is equal to r. We substitute this value in and get a final traction of 7 over 3 rho vector x. Similarly, for the outside the shell, we have our traction equation. We know that our normal vector is x divided by 2 capital R. We substitute this in. Again, x dot x is equal to r squared. We substitute in, and our function for f. To get this equation, we know at the outside shell that little r is equal to 2r. We substitute this in and get a traction of 0. Thank you.